The title of our case study is 3.3 Evaluating Determinants by Using Elementary Operations. Determinants in linear algebra are essential to comprehending the characteristics and actions of matrices. There are a number of ways to evaluate determinants, and one basic strategy is to use elementary row operations. We are able to methodically transform matrices while maintaining the value of the determinant by performing operations like row swapping, row scaling by constants, and row addition. Not only does using basic row operations make computing determinants easier, but it also provides important insight into the relationships and structure of matrices. For bigger matrices to be solved effectively, this methodological approach is not only necessary but also practicable. In this video, we examine the use of simple row operations in determinant evaluation.
The effect of the elementary row operations on determinant is as follows. Let A and B be square matrices and let K be a non-zero real number. First, interchange rows. Second, multiply a row with K. Third, add a row which is multiplied by K to another row. Note that the same effect applies for elementary column operations.
We can easily identify matrices where the determinants are zero by using a few simple rules as in the following theorem. Let A be an n times n matrix. Determinants of A equals to 0 if first, A has 0 rows or 0 columns. Second, 2 or more rows or columns in A are the same. And lastly, a row or column in A is a multiple of another row or column.
Purpose of study. First, to provide a clear view of the concept. Second, to obtain the determinants in the easiest way. Third, to evaluate determinants by using elementary row or column operation. Next, to identify matrices where determinants equal to 0. And last, to find the determinants for elementary matrices.
For case study 1, find the determinant of the following matrix using elementary row operation. We have matrix A equals to 2, negative 3, 10, 1, 2, negative 2, 0, 0, negative 3. For the first step, we replace the row 1 with row 2. As we know the effect when interchange row, so here we put minus symbol. The next step, row 2 plus 2 times row 1, since we add row with row that have been multiplied, so there is no effect. And the result, we have lower triangle matrix. With that, our operation is done. So, to find the determinant, we multiply all the elements along the main diagonal with the effect we got. Determinant of A is negative times 1 times negative 7 times negative 3 equals to negative 21.
For case study 2, find the determinant of the following matrix using elementary column operations. We have matrix B equal to 1, 0, 2, negative 1, 1, 4, 2, 0, 3.
First step, to change column 3, we need to minus column 3 with 2 times column 1. Second step, which is the last step before we get upper triangular matrix, is column 3 minus 6 times column 2, and the result will be 1, 0, 0, negative 1, 1, 0, 2, 0, negative 1. Since all the operations do not leave any effect, we only need to multiply the elements along the main diagonal. Hence, the determinant of B is the product of 1, 1 and negative 1 equals to negative 1. So that's all for case 2.
For this case study, we are going to prove that the determinants of the matrices are 0. First, A equal to 1, 4, 1, 2, negative 1, 0, and 0, 18, 4. So first, row 2 minus negative 2 row 1. The determinant will just be the same. There will be no changes. Row 1 will remain the same and row 2 is 0, negative 9, negative 2. And row 3 also remain the same. Now, as you can see, after performing one row operation which will just give us an equivalent determinant, for row 2 and row 3 have become one is a multiple of the other. Row 3 has become a multiple of row 2. After performing a row operation, we get a condition that makes the determinant is 0. And that is row 2 is a multiple of row 3. Therefore, the determinant of A is 0.
Case study 3. If 2i minus 4h plus 4gg, 2f minus 4e plus 5dg, 2c minus 4b plus 5aa equal to 8, find the value of a, b, c, d, e, f, g, h, I. Hence, find the value of minus 5d, e, f, minus 5g, h, I, and minus 15a, 3b, 3c. You look ABC now. This one, you have to interchange with row 3. Now, ABC is already at the first row, but the column is not. So, we can interchange column 1 with column 3. After that, column 3 multiplied with 1 over 2. Now, 4b minus 5a, it should be only b. So, column 2 minus 5 column 1, so you get negative 4a, negative 4e, negative 4h. And lastly, column 2 need to divide with negative 1 over 4, so you get BEH. Now, you have finished the ERO. Next step is to find a determinant. So, we start with 8 here. And interchange row, so negative 8. And interchange again. Negative sign change, 8. After that, you divide by 2. So, you will get 4 and then you use this operation, so the determinant remains. Next, you have to divide by negative 4. So, your answer is negative 1. We continue with hence find the value of this. So, first row, you interchange with row 3. Then, row 1 interchange with row 2. After that, row 3, you have to multiply with 3, so you get 3a, 3b, 3c. Next, the first column you multiply with negative 5, so we get negative 5d, negative 5g, negative 15a. Now, find the determinant. So, interchange row become 1, and interchange row again becomes negative 1 times 3, so get negative 3, and then times negative 5. The final answer is for this determinant is 15.
To sum up, we discovered that determinant values can be easily obtained by reducing any matrix of size n times n to a triangular matrix by using ERO. However, the process of reduction using ERO may be different, but the value of the determinant obtained will remain the same. On this topic, we also noticed that most of the elementary matrices are also triangular matrices, and hence their determinants can be easily obtained by multiplying the elements on the main diagonal. Therefore, evaluating determinants by using elementary operation is way easier if it is a triangular matrix.